Hello, I'm Rebecca Lewington from Cerebras Systems. I'm very pleased to be joined by Paola Buitrago, Director of the Artificial Intelligence and Big Data Group at the Pittsburgh Supercomputing Center, and Dirk van Essendelft, Principal Investigator within the Advanced Computing and Artificial Intelligence team at the National Energy Technology Laboratory. We're here to talk about some exciting work that promises to transform the speed at which we can perform computational fluid dynamics, which opens up a whole raft of new real-time use cases for this and many other core HPC applications. Paola and Dirk, thanks very much for joining me.
Thanks for having us.
Thank you, Rebecca, for the invitation. It's my pleasure.
And mine too. So Paola, kick us off. Tell us about PSC. What are you trying to achieve?
Well, the Pittsburgh Supercomputing Center is a joint effort of Carnegie Mellon University and the University of Pittsburgh. Our mission is to enable science and engineering discoveries for researchers that are advancing what is referred to as open science. As part of that mission, we had brought and made available to all the researchers across the United States to supercomputers like Bridges 2 and also neocortex. So in neocortex, as you all might be aware, we feature wafer scale engines and are exploring how can these great accelerators better serve our community. So both in the AI realm, but also besides the AI landscape. And today we will be talking about a great use case of these excellent accelerators that is not related to artificial intelligence.
Yes, people should be aware this is not about artificial intelligence today. But
Yet.
Yet.
Paola, what's your role? And tell me a bit about your background and your role at PSC.
Certainly. So my background, I am a chemical engineer and systems and computer engineer by formation, but then I have been with the Supercomputing Center for over 5 years now. So mostly on the director role, so I oversee projects and mostly in supercomputing, so Bridges at the time, Bridges 2 now, neocortex, and then other projects like Open Compass, where we basically were testing new technologies at the service of artificial intelligence.
You have some serious computational horsepower at your fingertips. Dirk, same question for you. Tell us a little bit about NETL.
Yeah, the National Energy Technology Laboratory, or NETL, is one of the 17 Department of Energy labs. We're one of the applied labs, and historically we've been the fossil energy lab, or been part of the Office of Fossil Energy, and now we're part of the Office of Fossil Energy and Carbon Management. So as the nation's priorities change here, we're kind of changing our role somewhat. So more of a focus on carbon management, and in addition to highly efficient chemical and fossil energy conversion systems.
So Dirk, tell us about your background and your role at NETL.
I'm a chemical and biochemical engineer by training, and I've joined NETL in 2009. And shortly thereafter, I joined the computational sciences division. And after the ImageNet competition in 2012, I really started focusing on everything AI related. So AI acceleration, and in particular, I've been interested in AI acceleration methods for partial differential equations. And so my primary two research areas are in advanced physics-informed neural networks and in hardware acceleration of both physics-informed neural networks and traditional scientific computing. And we're starting to now marry the two together. And I think in the wafer scale engine type systems, they offer some really unique advantages that we probably won't be able to take advantage of in any other kind of platform.
Yes, indeed. That theme of AI and HPC coming together is a recurring one. Now, I'm just a mechanical and electrical engineer, so please, I'm not one of the smartest people, so use short words. So let's start at the bottom. Dirk, what is CFD? What is computational fluid dynamics? And what's it used for?
Well, as the name implies, it's using computers to simulate the dynamics of fluid flow, right? So we're using computers to solve energy, mass, and momentum equations that determine how fluids move around objects, and that kind of thing. And so the CFD is actually really prolific in people's lives, even though they really don't know it. It exists in the design and engineering and even in post-production activities for really common things, from your household refrigerator to really complex things like what's happening inside of your engine when the piston fires, and simulating all of the fluid flow, drag around a car or a plane or whatever to make it much more efficient. It's really commonplace now in almost every kind of design and engineering for products that get sold. At the Department of Energy, we use CFD intensively to bring up the efficiencies and reactive intensities of energy conversion systems, or even in some cases we work in chemicals and stuff like that as well. Excellent.
Now, I understand that CFD is computationally intensive. Why is that?
It's the very nature of the equations that we're solving. In CFD and in general in field equation modeling, what you're doing is relating gradients in space. So like if you have temperature in your room and you were to measure the temperature at every point, it might have a certain value and it might have a slope to it, right? So we relate gradients in space to gradients in time. And that's really the heart of it. And it's the spatial gradient relationship that really drives the difficulty in CFD, because it makes it very data intense. So the actual calculations that we have to do there aren't very many calculations that we have to do in relationship to the amount of memory access that we have to do. And so any bottleneck that we encounter, whether that's to, if I'm a processor, if that's to my own memory over here or to my other processor over here, if I'm distributing it across the system, it creates significant bottlenecks that limit the speed, the looping speed that I can achieve. Right. And that's where this technology comes in.
Right. And following on from that, what's CFD not being used for because it's so difficult and so slow? Or put another way, what could we do if it were fast and easy?
Yeah, so really high fidelity CFD models can take months to run. And the higher the fidelity, and especially like if you're trying to run like Eulerian Lagrangian models and stuff like that, it can be very, very slow. And so we don't get to do very many of those types of things when we're doing like pre-production activities, like in design and design optimization and uncertainty quantification, just because it's not practical, right? It would take 10 years to run a very tight-knit design of experiments on, 1,000 simulations or something like that, right? So we end up doing, simplifying the models, making a lot of things, less accurate in order to make them run faster, right? And so there's always an accuracy trade-off and a penalty to pay for that to get the speed. So just to complete design optimizations and uncertainty quantifications, we already sacrifice, right? And because the solution speeds are so slow, it almost virtually eliminates CFD as a underlying model for real-time applications.
Wow, those are terrible trade-offs to have to make. Do I have the time to do this right, or do I have to get it out the door?
So Rebecca, I would like to add an example of one of the things that would be interesting to simulate with CFD. In particular, one interesting application of computing fluid dynamics is simulating the blood, right? So then there is research regarding like what happens with the blood in our circulatory system, like let's say all the coagulation cascade and whatnot. And what's going on with this type of simulations is, do you discretize the space? So it's as if, imagine you have an image and you have low resolution and then high resolution of images, right? Like when it's low resolution, you get a sense of what's going on in that image. But then if you increase the number of pixels, you'll get to see more details and really tell the story better. So that's what happened with CFD simulations. Like when you increase the resolution, you're able to analyze the system better in more detail. But also traditional approaches have been to just limit the space you're exploring because you want a certain level of resolution. And then you only say, I'm going to explore this little tube or this little vein that would translate to, I don't know, a certain size in real life. But then if you want to explore and analyze the system complete, then you need more and more compute resources and memory and whatnot. So then the moment we inject a better technology in these simulations, we are able to, on one end, go at a higher resolution, explore better the models and the systems, but also explore larger spaces all at once.
Yeah, and you can trade one for the other, right? You can trade fidelity for speed, and even on this new technology, we can still trade fidelity for speed, right? It's just that the boundary frontier is moved out by a couple of orders of magnitude.
Couple of orders of magnitude. That's a great lead into what we're here to actually talk about. It's pretty obvious where we're going with this conversation. Dirk, Paola, I think you may have just made CFD a bit faster.
It's possible.
Tell me more.
Yeah, so NETL applied for a grant for time on the neocortex and was awarded, and so we've had a collaboration going with Cerebras now for a couple of years to bring up a fluid dynamics package, and we got that running on the neocortex, and our first demonstrations were in a related problem, but we found that we were some 470 times, up to 470 times faster than what we could do on our Joule 2 supercomputer, which at one point was ranked number 52 in the world, I think. Since then, we've been working a lot with the team at PSC to solve a lot of, and you guys obviously in Cerebras, to solve a lot of technical issues that allowed us to get a full-fledged CFD simulation running. And I think we have a video out there now that shows this, and we're working with the Swiss National Supercomputing Center to characterize the same simulation and get the exact same results, but we're expecting it to be in the neighborhood of 200 to 400 times faster than what we measure.
Yes, indeed. The results are absolutely beautiful. I'll include, there's a link just here, and I'll include one in the description for this video too. So there are plenty of ways to get at it. So Paola, neocortex. Why neocortex for this?
Why neocortex?
Yes.
So neocortex features a new type of chip that it's beyond anything like that we have seen commodity hardware, let's say regular processors or GPUs. It just have all the elements that enable these kind of simulations at a faster speed and higher resolution. So it is very interesting, the work that we have been doing in collaboration with Dirk's team. So working on advancing the WFA. We are extremely excited regarding what else can be done, but not also by Dirk's team, but eventually making these resources and tools available to the overall CFD community. That would be of high interest. So certainly neocortex promises, and the buffer scale engine by Cerebras promises to be highly influential and impactful in advancing and kind of going beyond the border of what we currently can do on CFD in a timely manner.
Yes,
exactly.
Indeed. Yes, indeed. And Dirk, your collaboration with PSC goes back a bit, I think. Can you tell us something about that?
Yeah, I mean, NETL and PSC, we're all in the same neck of the woods here on the East Coast. So NETL has an office up in Pittsburgh, and we have another one down in Morgantown, which is where I'm based out of. And before NETL decided to invest in their own computing infrastructure, we had a long-standing relationship with PSC to do much of our simulation work at the facility there. In fact, most of the development in the early years of MFIX was done on PSC resources, and so yeah, I'm really excited to kind of revitalize this relationship and start working together again in a little bit closer way.
So now you have to tell me what MFIX is.
Oh, MFIX. Now you're going to stretch my mind.
You don't have to tell me what the words mean. Just tell me what it's for.
Oh, MFIX is our in-house CFD code, and it's really good at simulating fluid particulate flows.
Got it.
I have to say that I did some research and found collaborations going way back before the 2000s. So there have been collaborations on networking and also, providing access to the supercomputers that we had at the time. At the time, it was a supercomputer called Lemu that was one of the top supercomputers in the world back then. So there has been, several instances of like tight collaborations between NETL and the Pittsburgh Supercomputing Center. So certainly very excited to continue that legacy and continue exploring what else can we
excellent
use together. Yeah.
Dirk, I know we talked about this before, but could you just give us a quick potted summary of why the wave scale engine type technologies are better for CFD than traditional distributed supercomputers?
Yeah, it comes down to data bandwidth and latencies, right? So the wafer scale engine has a memory system such that I can always guarantee that I have 2 reads and 1 write per SIMD lane. So it's much like a L1 cache on a typical processor, but there are no other cache levels, right? So all system memory is within that 1 cycle reach of the processor. And that means that I can get to my own memory for data processing in a way that ensures that I never have a bandwidth limitation, right? Which is not true of any other kind of processor that has any kind of cache hierarchy. In addition, there's a router technology built. It's called a network on router or network on chip system that allows every processor to talk to its nearest neighbor, and it has the same essentially the same bandwidth and latency as if I'm getting to my own memory for 1 hop over. So that means that I can talk to my neighbors just as fast as I can talk to my own memory. And that together means that when we have a simulation distributed over the entire wafer, I see no memory bottlenecks whatsoever. The only kind of bottleneck that we would ever run into is if we do global reductions, right? And that would mean that every processor has to send their data to a central aggregator and then back out. But even that is still orders of magnitude faster than talking over a computer network. To put it in perspective, it takes about 1 to 3 microseconds to send a single bit of data across a network between 2 computers. And in that time frame, in about the same time frame, we can do a billion element reduction on the wafer scale engine.
A billion?
Yes.
And I should remind people that when Dirk's talking about processors in wafer scale engine type architecture, he's talking about adjacent regions of a single microchip, fractions of a millimeter apart, as opposed to meters, hundreds of meters between nodes in a conventional computer. So, Paola, how can other researchers take advantage of this work and take advantage of neocortex?
Absolutely. We are exploring ways in which we can bring the WFA toolset to other CFD researchers. That's to come, or we expect to have more news on that in the near future. But we also have and are preparing to announce a call for proposals where researchers doing both AI and other more fundamental science can come and leverage neocortex to advance their computing needs. And so please stay tuned. There will be a webinar where we'll be sharing, we will be sharing more details in terms of the models and kind of projects we welcome.
Super, you heard it here. If you're a researcher and you need some big horsepower, talk to Paola. Yeah. So, Dirk, what else can you do with the WFA?
Yeah, so the WFA is a general purpose field equation modeling software or partial differential equation solver. So if your problem can be broken up on a grid and your equations depend on nearest neighbors or a small neighborhood, this is the kind of ideal piece of software to help you get going on the wafer scale engine. It's what we're going to call a domain-specific language to this type of problem. And it has a front end that programs much like NumPy and Python. And in fact, the easiest way for people to develop a software right now is for them to write a very small problem in NumPy, and then it almost directly translates line for line into the WFA. And so it can be used for materials problems, structures problems, earth systems problems, computational fluid dynamics, electromechanics, electrodynamics. I mean, the kind of problems that we can solve, if you can write a differential equation for it, you can more than likely solve it through the WFA. And
That's a
be
lot
able
of
to
domains.
take advantage of this. Yeah.
That's a lot of domains to call domain specific.
Yeah.
Okay, amazing. And so just to finish off, Dirk, what's next for this work for you?
We're currently focusing on unstructured grids. So as one of my colleagues likes to say, the world is not structured; it's unstructured, right? And that's true in computational fluid dynamics, especially when you want to model things like turbulence. Boundary conditions are incredibly important. So the airflow going around my hand, if it's moving, we need a very fine cell resolution in order to capture the stronger gradients that happen, because it's at that boundary that sets up the larger eddy circulations downstream of this. And so being able to accurately represent the geometry through meshing in your problem is really important. And it's difficult to do that in a fully structured code like we have right now. So we're going to be transitioning the code base to support both structured, unstructured, and eventually I think we're going to be doing a hybrid system so that we can solve parts of the problem in a structured manner and other parts of the problem in an unstructured manner.
It's almost like you're distorting the mesh to have more voxels, whatever it is, at the points of interest, and then fewer.
That's exactly it.
That sounds like a difficult problem to solve, but one with tremendous computational efficiency benefits.
That's right. Yep. And so when you go from structured to unstructured grids, you suffer a little bit of a penalty because you have more indirection, right? Because you can't take advantage of ordering in the mesh necessarily. But you get the flexibility to easily give you the accuracies that you're really interested in. And so it's worth the penalty to slow down just a little bit in order to get you the accuracy benefits so that you can predict like turbulence, drag and stuff like that on a car, with very high accuracy.
Right. So far from being a narrow tool, this actually has a tremendously broad range of applications in the future, potentially.
Yeah.
Wow. So Paola, same question for you. What's next for you? What's next for Cortex, and what's next for PSC?
Yeah, certainly. So we continue to explore ways in which we can help researchers get access to powerful and transformative technology. So within NeoCortex, we expect to have at least 2 call for proposals this year. And then we are exploring making NeoCortex available through the overarching NSF program access. So that will be another way to get access to our system. Then there are other projects in the works that I cannot talk about just yet regarding making NeoCortex even more powerful and have even more capabilities, and also other projects that would be of interest. So once again, an invitation to stay tuned for what we will be offering very soon through PSC.
Great. Well, this has been very, very interesting, and also really for me, really quite inspiring. Tremendous new tools, tremendous new systems, tremendous new range of applications. If anyone's found this even remotely as interesting as I have, I recommend you get in touch and let's do some science. Thank you very much, both.
Thank you.
Thank you, Rebecca. Thank you, Dirk.